Hello everyone, welcome to AVLSI session number 11, part 2. And today we are going to continue our discussion on common source amplifier with source degeneration. So let's revise what we have covered last time. So last time we have seen the common source amplifier with source degeneration, and we attempted to derive the small signal voltage gain using Lima technique. So this was the Lima technique over here. So wherein we calculate the value of capital GM, transconductance of the circuit, and the R out, what is the output resistance of the circuit, multiply them together, and there we have it, AV, right? And we derived it under the assumption that lambda equal to 0, and we have ignored the body effect. So using this approach, we have found out the voltage gain of CS amplifier to be equal to minus RD divided by 1 upon GM plus RS. But this was with lambda equal to 0 and body effect being ignored. Now, in reality, that's a bad assumption, right? So we have to find the exact expression with lambda non-zero and body effect included. So that's exactly what we are going to do today. So let's begin. So following the same Lima technique, we will be deriving ahead. Let me adjust the screen. Yeah. So this is my common source amplifier with source degeneration. That means there is a resistor connected between the source terminal and the ground terminal. Now, since we have body effect present over here, because VSB is not equal to 0, we have the term GMB into VBS connected. And do you remember while deriving the transconductance of the amplifier of the network, we have considered output to be short circuited. So your output node is short circuited and we have disconnected the load over here, right? Then we put this inside, we will now analyze and find out the expression for I out divided by V in. Let me show it to you once more. What was that, Lima? Sorry for a second. Yeah. So what did we do for GM calculation? We short circuited the output node, and then we were supposed to find I out upon V in, right? To calculate capital GM term. So that's what exactly we are doing over here. First of all, we will disconnect the load. RED will not be present. Short circuit the output node over here, and call it as I out. And right now we have to derive a relation between I out and V in, which is nothing but your capital GM. Okay. So this is my small signal model of a degenerated CS amplifier excluding the load RD, right? So here the current entering the drain node is I out and the current leaving the drain node is also I out. And the voltage across this resistor RS will be VRS. So with this information, let us proceed forward. So now, right now, our aim is to find the transconductance of the amplifier, that is the GM. So GM will be given by I out into V in. So let's proceed with our derivation. Now we apply the KCL at the source node. So what do we get by applying the KCL at the source node? We have actually three terms over here. Okay, let me just slightly reduce it. Okay, so the current which is leaving the source terminal is I out, and all the other currents are entering the source terminal, which is GM into VGS, which is GMB into VBS, and there is one more current which is VDS divided by R out. Now here the voltage across the drain and the source terminal is VDS. So that's what we have written over here. I out is the outgoing current, and GMVGS, VDS upon RO plus GMB into VBS. So these three are the incoming currents at the source node. Okay. So now we will simplify it further. Now from the diagram, can we say that your VRS is actually equal to minus of VDS? Now what is VDS? VDS is the voltage across the drain and the source terminal. And and that terminal is connected to the ground. The drain terminal is connected to the ground, right? And over here, it's the same voltage in parallel because here the source terminal is common, right? So what will happen is your VRS will be equal to minus of VDS, right? That's what we have written over here. VRS will be minus of VDS, right? And what about VBS? VBS will be VB minus VS, right? And your bulk body volt terminal is connected to the ground. So VBS will be equal to minus VS. And what is minus VS equal to? Minus VRS. Okay. because the source voltage and the voltage across the resistor is one and the same. Fine. So let's continue from here. So we will rewrite this expression as I out is equal to Gm into Vgs minus Vrs upon R naught minus your GMB into VBS. VBS can be written as minus of VRS, right? And next, what do we do is we apply the KVL to the gate source loop. So what do we get by applying the KVL to the gate source loop? It says that V in minus VGS minus VRS is equal to 0. So can we write V in is equal to VGS plus VRS? Yes. So that's what we have written over here. V in is equal to VGS plus VRS. And what is VRS from the circuit diagram? Let us see that. So VRS is nothing but RS into I out. Okay, VRS is RS into I out. So that's what we will write over there. So VRS is I out into RS. So we can write the formula for VGS now. VGS is equal to V in minus I out into RS. And VRS is nothing but I out into RS again. So that means in the equation number 11.2.1, we substitute the value of VGS from 11.2.2 and we substitute the value of VRS from 11.2.3 in 11.2.1 equation. Okay, so we resubstitute the value, we substitute the value of VGS and we substitute the value of VRS from here. So what does it become? I out will be equal to GM times, here we have VGS, right? So what is VGS? V in minus I out into RS minus we have over here VRS. So instead of VRS, what do we write? I out into RS. So I out into RS divided by R naught minus again I out into RS divided by R naught into GMB. So this is the expression which we get from equation number 11.2.1, 0.2 and 0.3. Now from here we can see easily that all the terms of I out can be clubbed together on the left hand side and the GM into V in term can be pushed to the right hand side. Okay, it's already on the right hand side. So what do we get? If we divide I out upon V in, we get GM divided by 1 upon RS into GM plus GMB plus RS divided by R naught. Okay. So what is a capital GM? There's nothing but your I out upon V in, right? So your capital GM, which is your transconductance of your CS amplifier, which source degeneration is given by GM, this RO we have taken out, right? So we get capital GM is equal to small gm into RO plus RS plus 1 plus GM into GMB into RS, the whole into R naught. So if you multiply it and check it out, you will get this expression. Fine with it? Yeah. So this becomes equation number 11.2.4. So that's my exact expression of transconductance of my CS amplifier with source degeneration without any approximation and including the effect of lambda and body effect. Okay, so this is the derivation for GM. Now let's reduce it slightly. Yeah. So next what do we do is, next we apply certain simplifications. Okay. So what do we say is that RS value, it's very small compared to 1 plus GM plus GMB into RS into the whole into R naught, right? So we can ignore that term RS. This is just a simplification. Okay. The exact expression is given by 11.2.4. Now, so if we ignore the value of RS, the RO and RO gets cancelled out and GM will be approximately equal to GM divided by 1 plus GM plus GMB into RS. Now we know that the value of GM is very much greater than compared to GMB. So we can ignore the value of GMB and hence we write GM is given by approximately equal to GM upon 1 plus GM RS, which is the approximate value of GM. You remember in the last session, we have derived a similar result. See, in the last derivation, where lambda was equal to 0 and body effect was ignored, we got the same expression for GM. GM upon 1 plus GM plus RS. So that's exactly what we are getting over here. This is the approximated value of capital GM and equation number 11.2.4 is the exact value. Okay, this is more accurate. Fine. So this is about the capital GM derivation. Now we have to find the capital R out. Using the lemma, AV will be minus capital GM into R out. So let's do that. Let me slightly reduce this. So this is the first part. We have completed the derivation of GM using Lima technique. And now we will derive the output impedance of the CS amplifier with source degeneration using the Lima. So now again, when we do the output impedance, when we measure the output resistance of the circuit, what do? Let us check that in Lima. So we short circuit the input, that is we deactivate the input if it is a voltage, open circuit the input if it is a current. And yeah, we connect entire thing inside the box. And next we apply a test source at the output and measure the current through it. So the voltage source divided by the current will give us the value of R out. That's what the technique which we have adopted before. So yeah, putting everything inside the box and disconnecting any load connected. So right now we are calculating the value of R out, and then we'll at the end we'll put the load back, RAD back. Right now we are checking the the impedance looking at the drain terminal over here. Okay, excluding the load. If I include the load, I will have to I will do that later using the conventional small signal model derivation. I mean small signal voltage gain derivation. We will do that shortly. So right now this is the scenario. So we have short circuited the input V in, and we have applied a test source externally Vx and measured the current Ix. So my Vx upon Ix will give me R out. I mean Rx basically, right? So yeah, this is my small signal model for degenerated CS amplifier excluding the load. So yeah, so this current Ix entering the drain terminal will also leave the drain terminal and enter into the source terminal in the form of Ix only. Fine. So yeah, let's proceed forward. So we are deriving Vx upon Ix term. Let me just slightly, yeah. So from this diagram, what can we write? We write VGS is equal to minus Ix into Rs, right? Because here the gate terminal is connected to the ground and source terminal we have connected minus VGS, right? So your VGS will be minus Rs into Ix. So what will be VBS? VBS will be also be equal to the same thing, right? VBS also will be minus Ix into Rs. Now, how can we write Vx expression? So Vx expression can be written as Ix into Rs. Okay, so we can apply the normal KVL. So do we get Vx is equal to Ix into Rs plus Ro into, right? It has having actually two resistances. So yeah, let me just annotate and show it to you. Let me draw something over here. 1 second. So we have here, this is Ro. Okay, and we have another resistor Rx. This is going to the ground. So this is your resistor Rs. Okay, and from here we have Vx voltage. So this voltage is Vx, right? The current flowing through Ro will be different. I mean, will be same only, but yeah. And the current flowing through here, it will be Ix. Okay, so we have to write Vx is equal to, it will create two voltage drop, right? One will be the current flowing through Ro, right? And one will be the current flowing through Rx. Fine. So from this, let me just hold it over here. Yeah. So right now what we are doing is the current, the voltage Vx, it's generating a current Ix, which is flowing through resistor Ro. and that current flowing through resistor RO, it's basically the subtraction of Ix minus GMVGS minus GMB VBS. Okay, so the current flowing through RO will be Ix minus these two currents. So that's what we have written over here. The current flowing through this will be RO will be Ix minus GMVGS minus GMB VBS, and yeah, rest of the current flowing through RS will be Ix, right? So that's what we have written, Ix into RS. I hope it is clear. So Vx will be equal to voltage Vx will be equal to current flowing through RO, which is nothing but Ix minus Gm into VGS minus GMB into VBS plus Ix into RS. I hope it is clear. Okay. Yeah. So let me continue now. I hope that is clear now. So Vx will be equal to Ix plus RO into Ix minus Gm into VGS minus GMB into VBS. Now let us focus on this now. So VGS over here, yeah. So what we have written, VGS over here, it's basically minus Ix into RS, and VBS is also minus Ix into RS. So what do we get over here? Vx is equal to Ix RS plus RO into Ix plus, here the VGS will be minus Ix RS, so this will become plus Gm into RS into Ix plus, again plus sign because we are substituting VBS as minus Ix into RS, so plus GMB into RS into Ix, right, and the bracket close. And now we'll club the terms together of Ix. We'll take Ix common and put it on the left hand side. So we get Vx upon Ix is equal to RS plus RO into 1 plus GM RS plus GMB RS. Okay. So yeah, so this is the value of Rx which we are getting, which is equal to 1 plus GM plus GMB into Rx into RO plus RS. This is a very, very important result, which can be rewritten in the same form. So we have taken RO inside and you have taken RS here over here. So both expression 11.2.5 and 11.2.6 are one and the same. If you open the bracket, they one and the same, right? So it can be rewritten as Rx can be rewritten as 1 plus bracket GM plus GMB into RO bracket close into RS plus RO, right? So either way we can write it. So indirectly what it means is your degeneration, source degeneration has increased the output resistance. Okay. So effectively what we have done in this picture right now, what is this Rx actually? This Rx is the resistance looking into the drain terminal when we have sorted the value of V in as 0, fine, and also RS being connected at the source terminal, between the source terminal and the ground terminal. So what does this expression number 11.2.5 says? That it indicates that your RO output resistance of the transistor is boosted by a factor of 1 plus GM plus GMB into RS, and then it is added to RS actually. That is what it means. An alternate perspective can be equation number 11.2.6 suggests that RS is boosted by a factor 1 plus GM plus GMB into RO and then added to small RO, right? So any any way we can interpret it, right? So this is the exact expression of Rx. Now typically the value of RO is much greater than RS, right? So from the equation number 11.2.5, RS can be ignored, and hence we write Rx is equal to approximately equal to 1 plus GM plus GMB into RS, the whole into RO, right? But now we have to calculate the value of R out, not Rx, right? So R out will be a parallel combination of Rx and RD, right? So we know the expression of Rx now. We'll just put it in parallel with RD and we get the value of R out. Fine. So up till now we have not put the value of RD, load resistance. So when we put the load resistance back, what do we get? We get R out is equal to Rx parallel to Rd. So, we have two resistance in parallel. What do we get? Rx into Rd divided by Rx plus Rd. So this R out will become this huge expression, which is given by equation number 11.2.8. So that's the value of the output resistance of the amplifier of a common source amplifier, including the source degeneration effect. Fine. So this is the exact expression for R out. Very, very important. So let's revise what we have done so far. So we were determining the output impedance of the amplifier using the Lima technique. So we have disconnected the load and we were finding Vx upon Ix, that is Rx. So we found out the value of Rx, and now we included the load resistance. So R out will be equal to Rd parallel to Rx, and we found out the expression of R out, which is given by equation number 11.2.8. Okay, so that is how we derived the expression for R out, and earlier we have derived the expression for GM, exact expression for GM. So here it is. Okay, and now we have to just club them together, right? And that will be it. We have derived the small signal voltage gain using Lima technique. So now the small signal voltage gain using the Lima technique of a common source amplifier with source degeneration is given by this. So we have individually found the expression of GM, individually found the expression for R out. So according to Lima, what is AV, small signal voltage gain, minus capital GM into R out. So we substitute these values over here, and we found out that this expression over here in the denominator and this expression in the numerator cancels out. Okay, you can check it out. It cancels out. And yeah, finally, the exact expression of the small signal voltage gain of a common source amplifier with the source degeneration is given by expression number 11.2.9, as you can see over here, which we have boxed it. Okay, so this is the exact expression without any approximations. So last time when we have derived the approximated formula. Here it was. This is the approximated small signal voltage gain, assuming lambda equal to 0 and body effect being ignored. Okay, this was very simplified form. But in reality, this is the actual expression of the small signal voltage gain for a CS amplifier with source degeneration. Okay, so in short, what we have done is, for a common source amplifier with source degeneration, according to Lima, we have first find out the transconductance of the amplifier, which is capital GM. Then we found out the output impedance of the amplifier, which is capital R out. And then we wrote AV is equal to minus GM into R out, right? And we found out the exact expression of the small signal voltage gain for CS amplifier with source degeneration. Okay, so I think this was the last topic of this session. Yeah. So I hope that this is clear, and this is a very, very important point over here, that exact expression and approximated expression, there are huge changes. So in the numerical, if they ask you to find out the voltage gain, please note the note in the statement that if they have given lambda equal to 0 and body effect equal to 0, then you can use this formula. Okay, and if they have given the value of lambda and they have given the value of gamma, that is indicating that there is body effect, then we have to use this exact formula to calculate the small signal voltage gain. Okay, so I hope that you'll have following the steps. If you have any doubt, you can ask your doubts in the comment section. So we have completed today's topic, that is deriving the small signal voltage gain for a CS amplifier with source degeneration. Okay, so that's it for today. Next time we will continue with this topic. So until then, have a good day and thank you.